SwayamPrabha. Digital India. Educated India.
Good afternoon. We will start our lecture today on some more important aspects of flow modeling. We took up this issue in our last lecture. We discussed certain aspects. We'll cover some more aspects today. But before we start our discussion, we will just recapitulate something from the last class. In the last class, we took up Burger's equation, implicit Burger's equation, and then we tried FTCS method on it. But while taking up the equation, we wrote a form as given in equation 3. We called it a conservative form, and then we tried to discretize equation 3 in conservative form. So omega in plus 1 minus omega in by delta t is the left hand side, and right hand side, as we can see, we have written in central difference. And then we considered one-dimensional space as given in the figure, and we are running from I equal to I1 to I equal to I2. So left hand side, basically we can write that is integral omega delta x running from I equal to I1 to I2 divided by 1 by delta t, and right hand side is summation of this quantity over the integral space. And if we do that, we can see that we'll be able to write simple algebra, this half summation of I equal to I1 to I2 u omega I minus 1 at nth level minus u omega I plus 1 at nth level. Now we have to substitute I equal to I1 in equation 4, then I1 plus 1, then I1 plus 2. This way we will go closer to I2. We can say maybe I2 minus 2, I2 minus 1, then I2. If we do these substitutions, we will see that the summation series that we'll get from expression 4 in right hand side, all intermediate terms, different values of i's, that means I equal to I plus 1, I plus 2, I plus 3, etc. Those terms generated from this expression will get cancelled out. Finally, we will get this term. Intermediate fluxes are all cancelled out. Left hand side remains same. Right hand side is half u omega I1 minus 1 at nth level plus u omega I1 at nth level. All intermediate fluxes, if you write systematically, you will see they will cancel out. Minus again half u omega at I2 nth level plus u omega at I2 plus 1 at nth level. That means then here u omega summation of whatever is value here plus whatever is value here, and minus basically u omega, again values at I2 and I2 plus 1. Now I1 is this point and I1 minus 1 is this. So I1 minus 1 plus I1 average is flux at here. Similarly, I2 plus 1 average is I2 plus half flux at this dotted line. So U omega flux at I1 minus half minus U omega I2 plus half at nth level. So equation 5 states that the rate of accumulation of omega I in R is identically equal to the net advective flux rate across the boundary of R running from I equal to I1 to I2. Thus, the finite difference analog of implicit part of equation 3, we can say, has preserved the conservative property. As such, conservative property depends on the form of the continuum equation. Since this form of equation 3, this itself is conservative form, so this preserves the conservative property. On the other hand, if we take non-conservative form, same Burger's equation, instead of 3, if we write 6, where we do not write it in conservative form, we write it in non-conservative form, then again we can apply FTCS. We will get this expression. Then again we can integrate this expression between I equal to I1 to I2. And then we will get this expression on the right hand side. And we can see the right hand side fluxes. If we apply summation I equal to I1 to I2 on such fluxes, ui omega at I minus 1, ui omega at I plus 1 at nth level. And if we keep on substituting I equal to I1, I1 plus 1, I1 plus 2 up to maybe I2 minus 2, I2 minus 1 up to I2, then we will see that intermediate fluxes will not get cancelled out. And the final expression will not be outlet flux in the domain minus in inlet flux. So, which we obtained in the earlier case. Hence, the finite difference analog, here we are calling equation 7, is unable to preserve the integral Gauss divergence property, that is conservative property of continuum. We discussed this conservative property and then said there are weak conservative form and strong conservative forms, and then we discussed about transportive property, and we also discussed about need of upwinding for the advection dominated flow problems. Now we will take up basically again Burger's equation, and we have written del zeta del t plus u del zeta del x equal to nu del 2 zeta del x2 for u greater than 0. Now for upwind scheme, we have seen for u greater than 0, we will write xi at ith location will be xi I minus xi I minus 1. So xi I minus xi I at n plus 1 minus xi I at zeta I at n plus 1 minus zeta I at n is zeta, not psi. Xi is slightly different. So zeta I n plus 1 looks slightly different. we have not used it here. And zeta I will use it later. Zeta I at nth level divided by delta t equal to, we have taken the inviscid part, minus u I minus u zeta I at n minus u zeta I minus 1n by delta x for u greater than 0 and u less than 0. If u is negative, then we decided to use I plus 1 minus I. So basically, if u is negative, we will use downstream point, and if u is positive, we will use upstream point. So again, we can write Taylor series expansion for temporal variable. That means zeta I n plus 1 equal to zeta I n plus delta t del zeta del t plus delta t square by 2 del 2 zeta del t2, etc. Similarly, in the spatial domain, zeta I plus 1 is zeta I plus minus, this is zeta I plus minus 1. So obviously this sign is then plus minus delta x del zeta del x, then plus delta x square by 2 del 2 zeta del x2, again plus minus del x cube by factorial 3 del cube zeta plus del x cube, etc. So this will, what we will do now, we will try to substitute in this expression. For example, in this expression, if we want to write zeta I zeta n plus 1 minus zeta I at zeta nth level divided by delta t, that means this quantity minus zeta I n by delta t will get remaining terms on the right hand side, which is getting truncated, and we will try to get this truncated series for this term, and see what happens. So if we substitute for here, basically 1 by delta t, whatever is expression here within bracket, zeta I at n plus 1th level minus zeta I at nth level, will get all this entire truncated series 1 by delta t. Similarly, 1 by delta x, then zeta I minus zeta I minus 1 or zeta I minus zeta I plus 1, whatever depending on the upwinding. If we want to write that, we will be able to write minus u by delta x del x of del zeta del x minus del x square by 2. We have taken for positive u. So basically minus u by delta x we are writing outside the bracket, and then inside the bracket zeta I minus zeta I minus 1. From here I will this entire truncated series we will substitute here plus diffusive terms, and then if we try to reconstruct the equation, we will see that left hand side will get del zeta del t, right hand side we will get minus u del zeta del x plus half u delta t 1 minus u delta t by del x del 2 zeta del x2, and diffusive term was already there, which is nu del 2 zeta del x2 plus other higher order terms. Now apparently after constructing this term, that means after multiplication, this first term is producing u del zeta del x, but second term we have written as u, you can see 1 delta x will cancel out, delta x 1 minus u delta t by delta x and del 2 zeta del x2. So basically, this term and the term which is coming out after approximating this term, the second derivative of time here and the second derivative of space here, from these two, whatever is the truncation, this is otherwise truncated. Now, if that is not completely ignored, then from these two terms we will get this. How? We'll explain in the next slide. So what we can say, that del zeta del t equal to minus u del zeta del x. On the right hand side, first term has been taken up. The last term is nu del 2 zeta del x2 is basically the viscous term which is already there. We have not disturbed it. We have written that here, nu del 2 zeta del x2. But we have got this additional term while reconstructing the equation, and we are writing this as nu e del 2 zeta del x2. So that means this is some effective viscosity or which is non-physical arising out of our discretization technique. This entire term half u delta x into 1 minus u delta t by delta x, this is taken as nu e, which is artificial viscosity. It is behaving like, since this second order term, behaving like a viscous term, but this viscosity is not a physical property. This is coming because of, if we rearrange the terms, the temporal derivative and the spatial derivative, that means first order temporal derivative, if we write the highest term of the truncated series, and first order spatial derivative, if we write highest term of the truncated series, if we can organize them effectively, we will get this term. But while doing this, see, from here getting del 2 zeta del x2 and u delta x square, 1 delta x will cancel out by 2, is very simple. U delta x by 2 into del 2 zeta del x2 is, if we open this bracket, we will get that term from this bracketed terms that comes from here, from the spatial derivative. But this term, second term, if we again open the bracket, rationalize quantities, second term is coming from the temporal derivative. How? We will say now. So this term, first of all, we can call this as artificial viscosity, and we can write this as half u delta x into 1 minus, we have seen in the last lecture that we can call this term u delta t by delta x as a Courant number. So this is half u delta x 1 minus Courant number. Now in deriving equation 5, what we did, this del 2 zeta del t2, del 2 zeta del t2, which was the having the highest contribution among the truncated series, we have written that del 2 zeta del x2 as u square del 2 zeta del x2. How? Because del zeta del t we can write as del zeta del x into del x del t, and del x del t, x is the spatial dimension, del x del t gives a velocity. So velocity into del zeta del x. Again, if we take the second derivative of it, we will be able to get yet another u and del 2 zeta del x square, So it will be u square del 2 zeta del x square. Exactly that's what we got here. Okay, u square del 2 zeta del x square. If you multiply this term outside the bracket with the terms inside the bracket, we will get multiplier of del 2 zeta del x2 as u square. So the non-physical coefficient of viscosity nu E leads to diffusion like term, which is dependent on the discretization process. So this nu E is known as the numerical viscosity or artificial viscosity. So when we are reconstructing, getting back the equation, effectively we are getting del zeta del t equal to minus u del zeta del x plus nu del 2 zeta del x2. This is a physical equation, but as if we are adding, when we are discretizing this way, basically we are effectively adding new artificial viscosity into del 2 zeta del x2. And the artificial viscosity is half u delta x 1 minus Courant number. Now somewhat if we look at it more critically, we can see that we got this because this discretization we started as with the possibility of u being positive. U being negative will give us the same conclusion, similar conclusion, not the same conclusion. But here u being positive, we are getting u delta x 1 minus Courant number. Now u is positive quantity. Courant number has to be less than 1. Now if Courant number for stability that we have seen. So if Courant number is less than 1, this quantity is a positive quantity and this quantity is a positive quantity. So we will see that this artificial viscosity is positive quantity and this will definitely make some contribution in the final numerical solution. Obviously our effort will be to reduce artificial viscosity in such a way that it doesn't influence the solution. Now this expression we got because we took unsteady state term also, that del zeta del t Full-Burger's equation, unsteady term. If it's a steady equation, unsteady term is not there, then we can clearly see there will be no Courant number and the effective viscosity will be this artificial viscosity will be basically half u delta x. C will be 0. Now let us consider a two-dimensional convective diffusive equation with viscous dissipation in both direction, that and we will use the vorticity transport equation and substitute zeta by omega, and our velocity ui and vi both are positive. So if we do that, the equation is del zeta del t plus u del zeta del x plus v del zeta del y equal to nu del 2 zeta del x2 plus del 2 zeta del y2. And then we are substituting the difference quotients. Instead of del zeta del t, we are writing del zeta ij at n plus 1th level minus zeta ij at nth level divided by delta t. And since ui is positive, we are upwinding it, we are involving downstream point, we are involving, we are involving upstream point. Zeta I u is positive, that is why it will be ij minus I minus 1j. Again, extremely sorry. Please recall that if u is positive, we will involve downstream point, we will involve upstream point. Basically, the if ij is the point of interest, then I minus 1j, the upstream point. That is what is upwinding. And if u is negative, we will involve the downstream point in the finite difference quotient. So here u is positive, so we have used ij minus zeta upstream point I minus 1j. Similarly, v is positive, we have written zeta ij and zeta I j minus 1 delta y, and then we have written nu the viscosity, and then right hand side the central difference. This is simple, zeta I plus 1j minus zeta ij plus zeta I minus 1j by delta x square. Similarly, zeta j plus 1 minus zeta ij plus zeta ij minus 1 by delta y square. And just the way we did in the last example, if we substitute, write the finite the partial differential equation and substitute the finite difference quotients by these terms, and then we bring the truncated terms and try to reconstruct back the equation, we will get then del zeta del t equal to minus del zeta del x minus v del z minus u del zeta del x minus v del zeta del y equal to nu plus nu artificial in x direction, so artificial viscosity del 2 zeta del x2 plus nu, this is physical viscosity, plus nu ey in artificial viscosity in y direction del 2 zeta del y2. So here artificial viscosity, if we want to write down the expression, we'll get half u delta x into 1 minus Courant number in x direction. That means we'll involve u velocity and delta x here, and again artificial viscosity in y direction half v delta y 1 minus Courant number in y direction, that means v delta t by delta y, and here u delta t by delta x. So what we can say that for two-dimensional equation, if we reconstruct the equation after having discretized through FTCS method, we will be able to see generation of artificial viscosity in both the directions, and those artificial viscosities are functions of respective Courant numbers in x and y direction. So now this is the conclusion. Again, I am repeating that for the next slide also, that artificial viscosity in x direction, artificial viscosity in y direction. In x direction, artificial viscosity is having Courant number in x direction u delta t by delta x, and artificial viscosity in y direction is having Courant number in y direction. Now if u equal to v, delta x equal to delta y, then CFL condition gives Cx equal to Cy equal to C, and both are less than half. This indicates that for a stable calculation, artificial viscosity will necessarily be present, and for a steady state analysis, again Courant number will not be there. We get artificial viscosity in x direction as half u delta x and in y direction as half v delta y. We have observed that some amount of upwind effect is indeed necessary to maintain transportive property of flow equations, while the computations based on upwind differencing, because this upwinding is needed for retaining transportive property that we examined in last class. Today we have not done that, but today we can observe that if we do upwinding, then there will be some amount of numerical viscosity. For unsteady problem, we can have seen the expressions for numerical viscosity. Steady flow problems also we have seen the expressions for numerical viscosity. So what viscosity does? The physical viscosity, it diffuses. So numerical viscosity also will diffuse the error, and this is called sometimes false diffusion, and obviously this is a source of inaccuracy. One of the plausible improvements is the usage of higher order upwind differencing method. So obviously we can see that transportive property is needed, and for transportive property upwinding is essential. But if we do upwinding, we introduce artificial viscosity or false diffusion. So these are the issues we have to learn in whatever way we approach a physical problem, either by finite difference or finite volume or finite element. These issues will always be there, like retaining consistency, retaining conservative properties, those we have discussed in detail. Retaining transportive property also we have discussed, but now we can see that for having transportive property we must have some amount of artificial viscosity. But yet another dichotomy we are entering into, that is, if we have artificial viscosity, then that will introduce false diffusion, inaccuracy, or whatever you call error due to artificial viscosity. So our target should be to reduce that. One of the very effective way of doing this is basically going for a method which is called second upwinding. The second upwind differencing, this is you will see built in all the commercial codes, like if you use Fluent, Star City, CFX, everywhere you will see the options of discretizations are given, and one of the options is second upwinding. Now what is second upwind method? I will discuss that. According to second upwind differencing, then again we are writing u into zeta. Zeta is a property being transported. It may be even u velocity, v velocity, w velocity, or temperature with the u component of velocity. So u zeta del x of that at I j point. We'll first write this is equal to u at the right, u r zeta r minus ul zeta l by delta x. Here r and l, these are right point and left point taking ij as the reference, look at the figure. Ij is the point of interest. UR is a rightward point that will be considered, called UR. This is between I and I plus 1j, and UL is the leftward point which is between I and I minus 1j. You can write east and west, whatever. Basic idea is this is between ij and I plus 1j, another is between ij and I minus 1j. Now UR we have written here very simply, we have taken uniform grid, so we can write Uij plus Ui plus 1j by 2, and UL is Uij plus Ui minus 1j by 2. These are the right point, right to the point of interest. This is left to the point of interest. Point of interest is ij. And we'll write the finite difference quotient at this point, ij point, del x of u zeta. And u is the carrier velocity, which is defined at r and l points. We have explained already this way. Now if zeta r will be, so we'll apply the philosophy of upwinding. Zeta is being transported, so if ur is positive, then zeta will be a point which is basically ij point, the point in the upstream direction. So ur is positive, so the point which is upstream point related to ur is ij point itself. So we will write basically, if ur is positive, then zeta r is zeta ij. Similarly, zeta r is zeta I plus 1j if ur is negative. Ur is negative, then will involve I minus 1 point. But if you are positive, will involve upstream point, which is ij point. And similarly, if ul is positive, then will involve upstream point ui minus 1j, zeta I minus 1j, and if again ul is negative, will involve zeta at zeta ij. So zeta l will be zeta ij. So this way, if both, see, and this is whether positive or negative, we can take our own choice, and we can easily perform this exercise for having positive r value, negative r, u are positive, u are negative, ul positive, ul negative. Now in this example which we have worked out, we have taken ur positive and ul positive. Then what will be del x of u zeta? 1 by delta x. U zeta, ur is given by uij plus ui plus 1j by 2. And if ur is positive, then zeta r should be ij, zeta ij. Minus then ul. So basic expression we have written here, ul zeta l. So ul is uij plus ui minus 1j by 2, and if ul is positive, then zeta l will be zeta I minus 1j. zeta I minus 1j. We have written it here, substituted. So now del x of conservative form, if we write u square. So we have written here the expression involving u and zeta, but zeta if it becomes velocity itself, so then we can write del x of u square at ij. So 1 by delta x, that we have written here equation 5, 1 by delta x. We'll substitute this value of u that we have already taken, ui plus 1 plus uij plus ui plus 1j by 2, and then zeta ij will be uij. Similarly, uij plus ui minus 1j by 2, zeta I minus 1j, we will write ui minus 1j. Exactly, we have written that. 1 by delta x, this is ur into ij, minus this is ul into I minus 1j. Then we have done some algebraic manipulations with for bringing about some specific concepts, but slowly we will discuss. 1 by delta x, this term we have written. uij, what we have done, we have added I plus 1j and subtracted ui plus 1j and divided by 2. So uij plus ui plus 1j plus uij minus ui plus 1j by 2. Value is written uij. Similarly, minus of this quantity uij plus ui minus 1j by 2 multiplied by ui minus 1j. So instead of ui minus 1j, we have what we have done, ui minus 1j plus uij, again plus ui minus 1j minus uij. If we write this and divide it by 2, effectively value is ui minus 1j. But we are writing in this way in order to get some specific form. So then all these 2's will, 2 into 2, 4, that will come out 1 by 4 delta x, and within the bracket now we can write uij plus ui plus 1j, and this term we can regroup. One group is uij plus ui plus 1j, another group is uij minus ui plus 1j. Just we are regrouping this. Similarly, minus uij plus ui minus 1j, we are retaining this term, but but the multiplication is being done with this bracketed term. So this bracketed term now we can write ui minus 1j plus uij plus ui minus 1j minus uij. So if we write it in this way, clearly we can see 1 by 4 delta x within the bracket. Here uij plus ui plus 1j square whole square, and this term will be obviously a plus b into a minus b, so a square minus b square, so uij square minus ui plus 1j square. Minus quantity, now look at the minus quantities. So this is ui minus 1j plus uij multiplied by this means ui minus 1j plus uij squared. And then this is again a plus b being multiplied with a minus b. So it will be minus ui minus 1j square minus uij square. So equation 6 we get. Now we will apply another philosophy on equation 6 itself. We will introduce a modulus sign. How? First term we don't touch, uij plus ui plus 1j square. But the second term, this term, essentially we retain the same term, but we place uij plus ui plus 1j. This is basically uij plus ui plus 1j into uij minus ui plus 1j. So this uij plus ui plus 1j, that part we place under a modulus sign. And uij minus ui plus 1j, this part which has contributed this part again we bring here. Similarly, what we do, the minus quantities. So here we do not touch this, we retain this as such. So ui minus 1j, ui plus uij square minus again, what we do, because how did we form this term? This term was formed by multiplying ui minus 1j plus uij with this term. So we separate out this term under modulus sign and separate out and write this term separately. So ui minus 1j plus uij under modulus sign, ui minus 1j minus uij. And not only we introduce this modulus sign, we also introduce a factor eta. Now these eta and modulus sign, they have their own role. Modulus sign has been put to make this equation free of this bias, because we started as ur greater than 0, ul greater than 0. So ul, this can be 0 greater than 0, this can be less than 0. Both can be locally positive or locally negative. So if you do a little exercise on your pen and paper, you will see that to introduce that sort of versatile character, that it doesn't matter if you write this way and program this way, locally anywhere velocity may become positive, may become negative because of flow separation, several other things. It will not affect, and it will eventually take the right value, positive or negative, if we introduce modulus sign here. And this makes us independent of whether ur is positive or negative locally, and this makes us independent of whether ul is positive or negative locally. And then this entire term, you can see, is multiplied by eta. Eta is a small numerical factor. If eta is 0, you can see this discretization is equivalent to then central difference discretization. Just what here, this is this minus this quantity, so it is exactly the central difference discretization. And if eta is 0, it is central difference. If eta is 1, then it is first order upwinding. And if eta is a fraction, it is in between first order upwinding and central difference. So eta brings about the upwind bias in the finite difference quotient. If eta is small, equation 7 tends towards centered in space. So it will be like central difference. So basically this formulation we can see that it is called second upwind. It is basically an expression while locally the velocity is becoming positive or negative. It get eventually sensitized, the discretization expression, and if eta is retained at a small level, say 0.1 or 0.2, usually it is kept at a very small level, either 0.1 or 0.2 or maybe below 0.3 definitely, and then it is quasi second order accurate. It is basically tending towards second order accuracy, but it has some numerical error, artificial viscosity. That is what I have written here. This upwind method was first introduced by Gentry, Martin and Daly in 1966. Some more, it is again this Los Alamos group, some more stimulating discussions on the need of upwind and its minimization has been discussed by Roche in his very famous textbook on CFD. Is probably the first formal textbook on CFD, Roche's book, 1972, who has first pointed out the second upwind formulation possesses both the conservative and transportive property, provided the upwind factor, that is eta, it is formally called donor cell factor, is not too large. In principle, the weighted average, this is also called weighted average differencing scheme, can as well be called hybrid scheme. Redby and Torrance, again in 1974, it's a very well-known paper, they have explained this as hybrid scheme, and as I mentioned, that its accuracy can be enhanced by reducing the value of eta. Now we will go for yet another very, very important discretization strategy. It is just like second upwinding. It is also very, very popular, and this is also built in with several commercial codes. So you can see that if u greater than 0, this is the del zeta del t, this is forward in time, and del zeta del x, the first order derivative, is written as basically upwinding is done. We are involving upstream point. Since u is positive, zeta I n plus 1 minus zeta I minus 1 n plus 1, but at n plus 1th level, plus central difference, zeta I plus 1 minus zeta I plus zeta I minus 1 by twice delta x at nth level. So at 1 plus n plus 1th level, we are involving upstream point since u is positive, and we are writing basically rearward difference, and we are adding a central difference term, again specially central difference term for first order derivative in at nth level. Now this is modified central difference in space, which is a converse solution. When the solution finally in a steady state, when zeta in plus 1 becomes zeta in, is reduces to a space-centered scheme. Now consider the diffusive term. Diffusive term is written as usual by central difference, but at n plus 1th level. So you can see the formulation has very strong implicit character. And then, because we are involving I is the point of interest, we are involving I plus 1 point, I minus 1 point at n plus 1th level, and the values which are all known values at nth level, they are transferred to the right hand side. So you can see, a coefficient, this coefficient after algebra, the values associated with zeta I plus 1 n plus 1 will be ai. The terms associated with zeta I n plus 1 will be bi, and terms associated with zeta I minus 1 n plus 1 will be ci. And we can revisit ai, we have written, but what are ai? If you calculate, it will be nu delta t by delta x square. Ci is u delta t by delta x plus v delta t, nu delta t by delta x square. Bi is 1 plus u delta t plus delta x plus twice nu delta t by delta x square. Now, sorry, this is not v, nu. This equation does not have v. In Microsoft Word, nu and v, while writing, they look almost same. One has to be very careful in understanding it. So here, of course, there is no v. These are all new. So, and di, the right hand side di is basically 1 plus u delta t by delta x into zeta in minus u delta t by twice delta x into zeta I plus 1n plus zeta I minus 1. So this, if you do plug in del zeta del t plus u del zeta del x equal to nu del 2 zeta del x2 in Burger's equation, you will get this, terms as ai, ci, bi, di, and final equation in initial notation will be a minus ai zeta I plus 1 n plus 1 plus bi zeta I n plus 1 minus ci zeta I minus 1 n plus 1. So zeta at ith point at n plus 1 time level is not known, but it is expressed in terms of zeta at the location of its eastern neighbor and at the location of its western neighbor. Right hand side is di, and since these are either property values or velocity or the variable value zeta at previous time level, at nth level, everything is known in di. Now if we keep on substituting I equal to 2, I equal to 3, I equal to 4, like I equal to 4 means this will be at zeta 4, this will be at zeta 3, this will be at zeta 5. So we will get again one matrix equation in the form of ax equal to b. A is the coefficient matrix which is known. X is the unknown vector, which are basically zeta i's at n plus 1th level, equal to b, equal to right hand side vector, which is fully known. And if we can invert this matrix, we'll get the full solution. The system of equation is also, we can see these conditions from here, that for Ui positive, Ai, Bi and Ci, all three are positive. It's clearly seen. And Bi greater than Ai plus Ci. So there is a diagonal dominance. This obviously you can well understand that if we keep on substituting I equal to 2, I equal to 3, I equal to 4 up to I equal to I max or whatever, this B will constitute the diagonal, principal diagonal, and A will first row it will be boundary condition, but subsequently it will contribute as a subdiagonal element. C will contribute a super diagonal element. So we'll get a tridiagonal matrix. Remaining terms will be 0, and will be, if by solving this we'll be able to know zeta I is at next time level. The system of equation is diagonal dominant and capable of providing a stable solution. As the solution progresses, that means u at ui at nth level tends to ui at n plus 1th level. Here u is symbolic, u or zeta or v or any variable. The convective term approaches second order accuracy. This method is often called deferred correction procedure, because this whatever artificial diffusion is introduced, that keeps on reducing when we are maybe from reaching from one level to another level. We may have to do 2 iterations or 3 iterations, but as or even in 1 iteration, finally when we will get the converged solution, we will get basically artificial viscosity minimized. So that is what is called a deferred flux correction procedure, deferred correction method. This method was first introduced by Professor Prem Khosla and Stanley Rubin. Stanley Rubin is a very well-known name in CFD. He was the founder editor of the very well-known journal Computers and Fluids. So they introduced this scheme in 1974. So with this, I will stop here today. We have already been acquainted with quite a few issues related to fluid flow modeling. We'll introduce a few more issues and higher order upwinding strategies in the next class, and probably then the introduction of finite difference method will be over. Similar way we will introduce finite volume and finite element, and as I have said, then we will take up real Navier-Stokes solvers using such finite difference, finite volume or finite element techniques. We will stop here today. Thank you very much. We'll meet in the next class. Thank you.